Chain rule. Recall the chain rule for functions of a single variable. If y is a function of x and x is a function of t, say y equals f of x, x equals g of t, then the chain rule says that if we differentiate y with respect to t, dy dt, we could do that by taking the derivative of y with respect to x and multiplying that by the derivative of x with respect to t. So dy dt is equal to dy dx times dx dt. I'm going to keep this single variable chain rule in the upper right corner so we could compare it to the multiple variable chain rules we're going to talk about now. So now suppose that w is a function of x and y are both functions of t. So w equals f of xy, x equals g of t, and y equals h of t. The chain rule in this case says that dw dt is the partial of w with respect to x times dx dt plus the partial of w with respect to y times dy dt. This is a natural generalization of the single variable chain rule. As another example of a chain rule, suppose that w is a function of the variables x and y are both functions of two variables s and t. So w is f of xy, x is g of st, and y is h of st. The chain rule in this case says that the partial of w with respect to s is the partial of w with respect to x times the partial of x with respect to s plus the partial of w with respect to y times the partial of y with respect to s, and the partial of w with respect to t is the partial of w with respect to x times the partial of x with respect to t plus the partial of w with respect to y times the partial of y with respect to t. These are just two specific examples of chain rules involving multiple variables. The chain rule generalizes, just as you would expect, to functions with even more variables. Let's try some examples. Now's a good time to pause the video, try these examples yourself, and then resume the video to check your answers against mine. W equals x squared y minus y squared. X is equal to sine t, y is equal to e to the t. Find dw dt when t equals 0. Let me just point out before we do this that there are actually two ways to do this. You could replace x and y in the first equation there by what they are in terms of t, and then just differentiate w with respect to t the way you would normally in single variable calculus. But this is a lesson about the chain rule, so we'll do it using the chain rule. The chain rule in this case says that dw dt is the partial of w with respect to x times dx dt plus the partial of w with respect to y times dy dt. The partial of w with respect to x is 2xy. Dx dt is cosine t. The partial of w with respect to y is x squared minus 2y. And dy dt is e to the t. Now, at this point, we could replace x and y by what they are in terms of t, x equals sine t, y equals e to the t, and then plug in t equals 0. But it's a little quicker to just figure out what x and y are when t is equal to 0 and plug those values in directly. So, for example, when t is 0, x is equal to the sine of 0, which is 0, and y is equal to e to the 0, which is 1. Plugging those values in, we get dw dt when t is equal to 0 is 2 times 0 times 1 times 1 plus 0 squared minus 2 times 1 times e to the 0, which is just 0 plus negative 2 or negative 2. Next one, z equals the square root of x squared plus y squared. X is equal to sine 2t, y equals cosine 2t. What is dz dt equal to? Well, by the chain rule, dz dt is the partial of z with respect to x times dx dt plus partial z with respect to y times dy dt. Let's just change the form of z for a second. Z is the square root of x squared plus y squared, which we could rewrite as x squared plus y squared to the half. So the partial of z with respect to x is 1/2 x squared plus y squared to the negative 1/2 times 2x, which we can simplify to 2x over 2 root x squared plus y squared, and canceling the 2's, we get x over the square root of x squared plus y squared. Dx dt is just 2 cosine 2t, a little chain rule there. And we could do something similar for partial of z with respect to y. That's, again, 1/2 x squared plus y squared to the negative 1/2 times 2y, which we can simplify as before to y over the square root of x squared plus y squared. And dy dt is negative 2 sine 2t, again, a little single variable chain rule going on there. Now, the square root of x squared plus y squared, replacing x by sine 2t and y by cosine 2t, we see using the standard Pythagorean identity that we just get the square root of 1, which is 1. So we could pretend those denominators are not there. We're going to replace x by sine 2t and y by cosine 2t. And we see that this all adds up to just 0. This makes sense because if you look at the original expression, z equals the square root of x squared plus y squared, and you replace x and y by what they are in terms of t, you see that z is actually just equal to the constant function 1, whose derivative, of course, is 0. Next one, w equals 2xy, x equals s squared plus t squared, y equals s over t. And we want to find the partial of w with respect to s and the partial of w with respect to t. By the chain rule, the partial of w with respect to s is the partial of w with respect to x times the partial of x with respect to s, plus the partial of w with respect to y times the partial of y with respect to s. So the partial of w with respect to x is 2y. The partial of x with respect to s is 2s. The partial of w with respect to y is 2x. And the partial of y with respect to s is 1 over t. Replacing x and y by what they are in terms of t, we have 2 times s over t, 2 times s, plus 2 times s squared plus t squared times 1 over t. Since the denominator in both terms there is t, we can add everything up in the numerators, getting 4s squared plus 2s squared plus 2t squared, or 6s squared plus 2t squared. So the final simplified answer is 6s squared plus 2t squared over t. Now, again, by the chain rule, the partial of w with respect to t is the partial of w with respect to x times the partial of x with respect to t, plus the partial of w with respect to y times the partial of y with respect to t. So the partial of w with respect to x, once again, is 2y. The partial of x with respect to t is 2t. The partial of w with respect to y, again, is 2x. And the partial of y with respect to t is negative s over t squared. That's a little power rule there. We could think of y as s times t to the minus 1, and the derivative is negative 1 s t to the minus 2, which we could rewrite as negative s over t squared. Once again, replacing x and y by what they are in terms of t, we get 2 times s over t times 2t plus 2 times s squared plus t squared times negative s over t squared. Here we need to get a common denominator. I'm just multiplying that first term by t over t so that we have t squared as the denominator in both terms. And we get 4st squared minus 2s cubed minus 2st squared all over t squared. Combining like terms there in the numerator, we have 2st squared minus 2s cubed over t squared as our final simplified answer. Next, we have w equals xy plus yz plus xz. X equals s cosine t, y equals s sine t, and z equals t. And we want to find the partial of w with respect to t when s equals 1 and t equals 2 pi. Now, we didn't formally write out a chain rule in the case where w is a function of 3 variables, but hopefully at this point you kind of see the pattern and you could figure out how to write the chain rule correctly. So here it is. The partial of w with respect to t is the partial of w with respect to x times the partial of x with respect to t, plus the partial of w with respect to y times the partial of y with respect to t, plus the partial of w with respect to z times the partial of z with respect to t. So the partial of w with respect to x is y plus z. The partial of x with respect to t is negative s sine t. The partial of w with respect to y is x plus z. The partial of y with respect to t is s cosine t. The partial of w with respect to z is y plus x, and the partial of z with respect to t is just 1. Now, as we did in the first problem, we're going to replace s by 1 and t by 2 pi in each of x, y, and z to get the corresponding x, y, and z values. So for x, we have 1 times the cosine of 2 pi, which is just 1 times 1, which is 1. For y, we have 1 times the sine of 2 pi. Since the sine of 2 pi is 0, we get 0. And for z, we just get t, which is 2 pi. Substituting these back in to get the partial of w with respect to t when s equals 1 and t equals 2 pi, we have 0 plus 2 pi times negative 1 times 0 plus 1 plus 2 pi times 1 plus 0 plus 1 times 1, which comes out to 1 plus 2 pi plus 1, or just 2 plus 2 pi. Let's now write out the chain rule for the case where w equals f of x, y, z, s, and t. X is x of uv, y is y of uv, z is z of uv, s is s of uv, and t is t of uv. Pause the video, try to write out the correct chain rule in this case, and then resume the video to check your answer with mine. There are two partial derivatives we could take. We could take the partial of w with respect to u. That's the partial of w with respect to x times the partial of x with respect to u, plus the partial of w with respect to y times the partial of y with respect to u, plus the partial of w with respect to z times the partial of z with respect to u, plus the partial of w with respect to s times the partial of s with respect to u, plus the partial of w with respect to t times the partial of t with respect to u. And similarly, we could do the partial of w with respect to v, and we get the partial of w with respect to x times the partial of x with respect to v, plus the partial of w with respect to y times the partial of y with respect to v, plus the partial of w with respect to z times the partial of z with respect to v, plus the partial of w with respect to s times the partial of s with respect to v, plus the partial of w with respect to t times the partial of t with respect to v. Implicit differentiation. The multivariable chain rule provides us with a nice way to do implicit differentiation that's a little less tedious than the way that you learned in single variable calculus. Starting with w, a function big F of xy equal to 0, where little y is equal to f of x, we see that what we have here is y is a function of x, but the expression f of xy equals 0 is defining y implicitly in terms of x. In other words, y is not by itself in this equation. The x's and y's are mixed up together in the equation. So if you remember in single variable calculus, you learned a method called implicit differentiation to be able to find dy dx even though y was not by itself. Now we're going to derive a formula that gives us a simple computation to do this as well. So differentiating each side of the equation w equals f of xy, and using the chain rule, we have dw dx is equal to the partial of big F with respect to x at xy times dx dx plus the partial of big F with respect to y of xy dy dx. Now, dw dx is just 0 because w is 0, and dx dx is just 1. So the expression simplifies to 0 equals the partial of big F with respect to x at xy plus the partial of big F with respect to y at xy dy dx. And we could easily solve this for dy dx by subtracting f sub x from each side of the equation and then dividing by f sub y. So we see that we can compute dy dx simply by taking the negative of the partial of big F with respect to x at xy divided by the partial of big F with respect to y at xy. This is the implicit differentiation formula involving partial derivatives. Let's try some examples. Go ahead and pause the video, try these examples yourself, and then resume the video to check your answers against mine. And the first one, y cubed plus y squared minus 5y minus x squared plus 4 equals 0. Notice that y is defined implicitly in terms of x because y is not by itself in this equation. But we could easily compute the derivative dy dx by applying the implicit differentiation formula that we just derived. We get on the top the negative of the partial of this expression on the left with respect to x, which is just the negative of negative 2x, which is 2x. And on the bottom, we take the partial of the left-hand side of that equation with respect to y, and that's just 3y squared plus 2y minus 5. For the second one, we could apply the same formula. So the partial of z with respect to x, on the top, we take the negative of the partial of f with respect to x, and we see that the partial of f with respect to x is 6xz minus 2xy. Since we're taking the negative, I'll just interchange the two terms and write it as 2xy minus 6xz. On the bottom, we take the partial of the left-hand side of that equation with respect to z, and we get 3x squared plus 6z squared plus 3y. Similarly, for the partial of z with respect to y, on the top, we take the negative of the partial of f with respect to y, where f is the expression on the left-hand side of that equation. The partial of that with respect to y is negative x squared plus 3z. We negate that to get x squared minus 3z. And notice the denominator is exactly the same as in the partial of z with respect to x, because it's also the partial of the left-hand side of that equation with respect to z. Another example, find y prime if 2x cubed plus 3y to the fifth equals 4xy. Pause the video, try this yourself, and then resume to check your answer with mine. Okay, we first need to bring that 4xy to the left-hand side of the equation. So we'll let capital F of xy equal 2x cubed plus 3y to the fifth minus 4xy, so that that equation has a 0 on the right-hand side. And then dy dx is the negative of the partial of this expression f with respect to x over the partial of f with respect to y. The partial with respect to x is 6x squared minus 4y, so that goes up top. And the partial with respect to y is 15y to the fourth minus 4x, so that goes on the bottom. One more example. Find partial of z with respect to x and partial of z with respect to y if x plus y squared plus z cubed plus xyz is equal to 3. Once again, pause the video, try this yourself, and then resume the video to check your answer. Again, technically speaking, we should bring the 3 over to the left to get the expression f of xyz is x plus y squared plus z cubed plus xyz minus 3 equals 0. However, since the right-hand side is just a constant, it actually doesn't matter if you leave it there because that's just going to differentiate to 0 anyway. In any case, the partial of z with respect to x is negative the partial of f with respect to x over the partial of f with respect to z. The partial of f with respect to x is just 1 plus yz, and the partial of f with respect to z is 3z squared plus xy. Similarly, the partial of z with respect to y is negative of the partial of f with respect to y over the partial of f with respect to z. The partial of f with respect to y is 2y plus xz, and we already saw that the partial of f with respect to z was 3z squared plus xy.